This video is going to cover the basic instrument settings and documentation I use when monitoring vibrations during geophysical operations. If you want to skip ahead to the disclaimer and get right into it, the time is listed below. I'm going to cover the basic instrument settings and give some examples. I'm not going to read every slide, as you can simply pause the video to review. A lot of this will be focused on seismic vibrators, but dynamite settings are essentially the same. The main difference is vibrators are generally a longer but smaller energy event, and dynamite sources are instantaneous. I also plan on creating short videos on sensor coupling and orientation, setting up a test program, reviewing, analyzing, and displaying the data, and how we used vibration test monitoring to change the geophysical distance requirements from specified structures in Alberta. In the geophysical world, we use explosives, seismic vibrators, and other impulsive or passive sources. Our concerns are generally the same as construction and blasting operations: potential damage to structures or other unintended consequences. So why am I doing this? I haven't seen anything on this topic specifically, and secondly, because I have seen some things in the field that suggest this could be helpful. I know there are vibration monitoring courses, but I'm not aware of any that are specific to geophysical exploration. So consider this a bit of an introduction. I'm going to speak in general terms, as geophysical parameters can be highly variable. But suffice to say, we design our energy sources to be fit for purpose, and we need to get close to structures to ensure we get good subsurface imaging. These structures could include residences, water wells, pipelines, piezometers, dams, developed springs, power lines, fiber optic cables, to name a few. The one thing I want to share about geophysical operations is the fact we may do several thousand source points in one 12-hour shift. And those source points are often scattered 360 degrees around every structure of interest or concern. This could be over 3 events per minute. This will come up in more detail when I discuss sensor orientation and analysis. When we use dynamite, we usually load an explosive charge in a hole ranging from 3 to 18 meters deep, with the explosive charge ranging from 0.125 of a kilogram to 8 kilograms. We drill and load the holes and leave them for when we record later. We usually detonate one charge at a time to create one seismic record. With vibrators, we may use a single small 15,000-pound vibrator or multiple 60,000-pound larger vibrators. We generally sweep a frequency range starting at about 4 Hertz and increasing to about 150 Hertz over about 20 seconds. All of these variables are subject to change, and these are just examples. Small vibrators are generally used for shallow targets, but that is not always the case. So here is what an increasing vibrator signal looks and sounds like. And this is what the signal actually looks like. And on the left is the start of the sweep, where we have an amplitude taper on the sweep starting at a lower frequency, and we increase to higher frequencies. And on the right hand side, we've achieved the higher frequencies, and then we generally taper down the amplitude to the end of the sweep. And so in this presentation, I'll get some things correct, I'll get some things wrong, and that's where you come in with a comment, feedback, or a question. I should also note many of the slides are extracted from my document on geophysical PPV monitoring, and the figure numbers may be out of sequence. Now, before we begin, here is a caution, a truth, and a disclaimer. First, a caution. If you have an operating procedure you are using, this is meant as a discussion piece. I am not advocating you change your procedures. I am advocating continual improvement. Do your due diligence before you make any changes to your process. The truth? This video has nothing to do with Instantel. I just happen to use their equipment. This video is not sponsored, endorsed, nor has it been reviewed by Instantel. I am just sharing my geophysical experience. And finally, the disclaimer. I am not a certified trainer, nor have I had any formal training. This is a discussion piece for consideration, and it is not instructional. Again, this is a discussion piece. I am not advocating you change your procedures. Okay, so I typically use a Minimate Pro 4 with extended memory, but this is geared mainly toward the Micromate unit and the Instantel Thor software. With the various circumstances, you may want to do things differently. I get it. My standard is waveform monitoring, but I may also use histogram combo for specific reasons. The first thing I do with the instrument is to make sure all the background settings are correct, as they will become part of the file. The two most important things are time and date. You have to decide if you want to use local or GMT. Most seismic recording is done in GMT, but as long as you know the time offset and it is documented, you are fine to choose either. Make sure any clock errors are documented, such as the instrument time being 5 seconds slow compared to the actual time. The other settings to enter correctly are location, client, company, operator, job number, and general notes. Sound pressure levels are generally not a consideration for geophysical operations because of our smaller charge sizes, distances from the structures, and we generally shut down in the evenings in residential areas. So this slide is my recommended starting point. This is the cover of the ISEE guidelines for blasting seismographs. The guideline has been developed by experts and has been continually refined over the years. Any basic instrument deployment protocol should follow this methodology. There is a link to this document in the description. So let's get started. I trigger on vibration, and the microphone setting is usually disabled. For recording, I select waveform. I may use histogram combo on occasion, but for most geophysical applications, I use waveform. I have seen operators use waveform manual, but at times have either failed to do the sensor check or missed the onset of the event entirely. For vibratory size or induced seismicity monitoring, I use auto and not fixed time recording. Fixed time means the instrument stops the data record at that specified time after the instrument has been triggered. I may consider fixed for dynamite, but I usually do not. I select auto stop after, and I typically use 2 or 3 seconds, but I could go longer. This figure here shows that the vibrator signal fell below the threshold value and continued recording for the selected auto stop time after. It is very common, if the vibrator is greater than 10 meters away, to not record the entire sweep, as the initial vibration may not be high enough to trigger the start of recording, and the higher frequencies during the latter part of the sweep often do not generate much surface vibration. But all of this depends on the sweep, the drive level, the distance, the size of the vibrators, and ground conditions. Now here's a warning for people that may also be measuring sound pressure. You might have to wait some time for the sound pressure wave to arrive. Here is an example of a 5-second delay for the sound pressure wave to arrive.
Arming. Okay. We are armed. Firing in 3, 2, 1.
For geophone trigger level, I will set the threshold just above the background noise level, which is usually between about 0.35 to 0.5 millimeters per second. In production recording, I may set this a bit higher to reduce the potential of false triggers. For pre-trigger in dynamite mode, 0.25 seconds is fine. For vibra size, often you will want a longer pre-trigger. Now this is not absolutely necessary, as the vibration level is very low, but to actually see how the vibrators are performing and when they are triggering the instrument, it can be helpful. As a geophysicist, my preference is to record as much data as I can. I should note the Minimate Pro has an automatic 0.25 second pre-trigger, and the Micromate has several options from 0.25 seconds up to 1 second. Once that instrument is in waveform monitoring, it is collecting data. When it has a vibration greater than the threshold level, it records an event. Because the instrument has been monitoring and storing the data in a buffer, the instrument can go back in time and start at the selected pre-trigger time. That means if my trigger threshold is at 0.3 millimeters per second, it is reached at time 0. But the data associated with the event starts at minus 0.25 seconds, and you will see all the preliminary events and then the 0.3 millimeter per second event at time 0. For people not familiar with vibra size operations, I thought this next figure might be helpful. This describes the reality of hydraulic vibrators trying to get low frequencies into the ground. In this example, you can see the AHV4 380, which has a peak force and a hold down weight of 80,000 pounds, only transmits 23,000 pounds at 3 hertz. This does not include any sweep taper that we selected, which can further reduce this level. This means the low frequencies we are usually concerned about because of the compliance curves is helped by the fact that vibrators are limited in their hydraulic delivery limitations. Imagine the hydraulic fluid flow just to move this 3,600 kilogram mass. Now imagine you would like it to deliver a full 80,000 pounds force at that type of displacement. It is just not possible. For sample rate, I typically use 4,096 samples per second. This figure shows the instruments measuring the same vibrator sweep just a few meters apart. The data on the left is using 1,024 samples per second, and the one on the right is using 4,096 samples per second. Here is the other reason I use 4,096. There can be some potential error in the frequency of up to 5 Hz in the 31 to 50 Hz range, which can be important. As looking at a compliance curve, you can see we definitely do not want to have errors in this range as we are trying to stay below this Z curve. Sensor check is something else you have to get correct. I have seen this approached in very strange ways over the years, and even the ISEE say the sensor should be nearly level, but leave it there. So I use a level to place the instrument. Any axis that is not level will affect at least one other axis. Okay, I'm just going to do a backyard demo as to why getting the sensor level and having your sensor check protocol correct is so important. So if I am just going to install this instrument in my backyard and aim the longitudinal axis towards the source point, I may do it like that. But it's fairly hard to get the level or the sensor correct unless you're using levels. So I always use a 2-axis level and use that to get it properly mounted and secure. You can use a single bubble level and just move it back and forth until you're correct, but that's typically what I would do. So then I would do a sensor check on this, and so it'll pulse all 3 sensors and compare the results with what it expects, and in this case I can see it's passed on all 3 axes. So now if I was expecting a lot of acceleration in and around this sensor because I was very close to the source, I would probably sandbag the sensor, and then I would redo a sensor check. But let's go into start monitoring. So for geophysical operations, I have selected sensor check before event. So it's going to go through the sensor check process here, and then it's ready to monitor. And I've got this set to trigger at 0.3 millimeters per second, and once it falls below that threshold, it will continue recording for another 3 seconds. So if I just tap it on top and I do a waveform record there, it will start collecting the data. Don't worry about the first number you see, it's not part of this. And there I see 8.61 millimeters per second, and all of a sudden I could have another event coming, and it could be hitting this longitudinal axis, and it's recording, and I stop with the vibration, and 3 seconds later my recording stops. So I would continue recording throughout my day, and we'll stop. And now let's have a look at the data files. Now the very first one, we know we triggered on vertical, and we can see that. We can get the results. But the important thing I want to show here is along sensor check, it's saying pass, pass, pass. So I actually have that information that it's passed on all 3. And we can go to the second event, which was part of the same thing. On that one, if you remember, I triggered it on the longitudinal axis, so we have that. And again, we've got the pass, pass, pass. So that information that the sensor check passed before we started our recording is very important for with your data. So now this is part 2, and this is going to have a sensor that is not level for whatever reason, but it's simply not level. Maybe I pulled on the cable after I thought I got it set up, or maybe I just was on very, very uneven terrain and I couldn't get it correct. So let me do the sensor check with it like this. And it will do the sensor check repetitive times. I think maybe the first time it thought maybe there was a bit of a noisy event and it didn't pass, so it's trying to do the sensor check again and again and again. And finally it realizes it's not correct, and it's saying check all 3 axes to make sure it's better. So, let's say I just come and I go, yeah, you know what? I think I've got it now. And I'm going to do my monitoring. So I do this. I know it's going to do a sensor check before event. It's doing that. Now let's say I leave and I'm talking to somebody, or I go to my truck for something, or I'm focused on something else. I may not recognize that it is going through the sensor check numerous times. And it's repeating it and repeating it, just like the previous time when it failed. But now the instrument goes into waveform monitoring. So if I come back, I'm going to assume, it's ready for monitoring. So once again, I have an event happen, and I'll tap it on the vertical axis. It's recording, and we will get our result here, 16 millimeters per second, and we have that. So I could go on and continue recording, event after event after event, but let's go down and have a look at this data file. So we'll come down to this last one we did, triggered on the vertical, and we'll have a look, and I can see that it had passed on the transverse, passed on the vertical, but it failed on the longitudinal axis. So when you're going to demonstrate to somebody that we are confident that the level of vibration was lower than a certain threshold, but your sensor check actually fails, you're not going to be in a very defensible position. So that is why having your protocol absolutely correct is very important. So then lastly, if I've been away from the instrument and I approach it very carefully and it's still monitoring, I will touch the enter button here, and I can see it is still waveform monitoring, and I'm about to complete my recording for the day. So I may do one final tap on the sensor and make a final record and document this, that it was done and at what time. And then I will shut off the instrument. And then as it sits there without doing anything else, I will do another sensor check to the instrument. And here it pass. So I will document that in my notes to show that my sensor check at the beginning passed, and then when I completed my work, the sensor was still in a position and secure and passed. And that's pretty much my process. Then lastly, on setup, I may decide to remove the offsets if I'm in a quiet environment. You should read up on this yourself. Now, here are the slides on basic documentation. I'll leave them up for a couple of seconds. If you want to review in detail, simply pause and take notes, or you could email me and request a copy of the PDF. My email contact information is in the description. And then finally, because I just happened to have it in this video file I was making and didn't have an easy way to store it and then put it in another video, I'm just going to show you some coupling issues working with a quarry blast, just for something to look at. Anyway, thanks for taking the time. If you've got any comments, please leave them or reach out and we can have a further discussion. I'd like to improve this video. Thank you.